Okay, so we're going to start talking about graphs of logarithmic functions and thinking about how we might transform them or what they might look like in different situations. So before we do that, let's just remember exponential functions, right? So exponential functions, think of one in your mind. It has a horizontal asymptote at the x-axis, right? And if b is greater than 0, it increases. If b is less than 0, it decreases. In either case, the domain is negative infinity to infinity, and the range is 0 to infinity, right? As we talked about last time, this is the inverse of the exponential function. So we know the domain and range are going to flip, right? So the domain is the range of the exponential, 0 to infinity, and the range is negative infinity to infinity. So what does that mean? The domain, or what x values this is defined for. The domain goes from 0 to infinity. Okay, that means the only things we can take logarithms of are positive numbers. The range, anything could come out, but the only things we can put in here are positive numbers. This is almost like square root functions, right? So other domains we've had to worry about are like can't divide by 0, can't take the square root of a negative number. Now we've got another one. We can't take the log of 0 or less, right? This input has to be a positive number. So if we had this question, what is the domain of this log function? Well, we know that x plus 3 has to be greater than 0. So pretty easy inequality to solve. Right? So the key point is recognizing that this has to be greater than 0. So the domain is going to be x greater than negative 3 or negative 3 to infinity. Right? How about this one? What is the domain of this log function? So log base 10. Well, we know it doesn't matter what the base is, right? Whatever the base is, we know this has to be greater than 0. So we can just set up an inequality. 5 minus 2x is greater than 0. We solve that x has to be less than 5 halves. And the domain is going to be negative infinity to 5 halves. All right, so what's the graph really going to look like here? So let's make some tables just to get an idea. So if we have these x values, negative 3 going up to 3, and we have this exponential function, 2 to the x equals y. Well, 2 to the negative 3 is 1/8. 2 to the negative 2 is 1/4. Right, all the way up. 2 squared is 4. 2 cubed is 8. Right? Well, the inverse is going to give us the other thing out. Right? If this is our y value, this is going to be our x value. Right? So what does that really mean? We have these ordered pairs, negative 3 1/8, negative 2 1/4, right? For the exponential function, the order is going to be switched. This is going to be our x value. This is going to be our y value. This will be our x value. This will be our y value. The x and y values switch for inverse functions. Okay. So these are going to be the points that we plot, and we can look. Here's the exponential function 2 to the x. Then our log function is going to look like this. Yep, and they are a reflection about this line y equals x, which we'd expect. That always happens for inverse functions. All right, so let's look really carefully at these. Here's the log function if b is greater than 1. And here's the log function if b is between 0 and 1. So remember, the exponential functions looked really different, right? If b is greater than 1, it looks like it goes up like this. And if b is less than 1, it goes down like this. Okay? So it's 1 to 1, just like the exponential function, so they both are invertible. So in both cases, there is a vertical asymptote at x equals 0. Right? The domain for both is 0 to infinity. The x-intercept is 1, 0 in both cases. And that's because, right, for our parent function e to the x, or b to the x, our y-intercept is 0, 1. Right? So that gets reflected. In both cases, the x-intercept is 1, 0. And the key point is b1. Okay, in both cases, b1, b1. So here b is greater than 1, here is less than 1. Okay, because that's asking the question, If x is b, b to what power equals b? 1. B to what power equals b? 1, right? So that is a key point. That gives us, we have a vertical asymptote, a x-intercept, and the point b1 in both cases. So let's see. There's no y-intercept in either case because that's the vertical asymptote. It is increasing if b is greater than 1, right? This graph is increasing, and this graph is decreasing. So it's decreasing if b is between 0 and 1. So those are all important things we're going to use when we think about transformations in just a minute. All right, so let's look at changing the base b. What happens? So this is log base 2. Okay, again, all three graphs, and this is the blue is natural log, so base e, and the orange is log base 10. So let's see, these are going and increasing. The bigger the base, the flatter the graph, right? And in all cases, they go through this, the x-intercept is 1, 0, right? And they all go through the point B1. So this goes through the point 2, 1. This goes through the point 2 point whatever 1 for E, whatever E is. And this goes through the point 10, 1. Okay, or 2.7. 2.7 is where it crosses it, 2.71 for E. Okay, so what if we want to graph this? Log base 5 of x, and then state the domain, range, and asymptotes. All right, so this is going to be like our parent function. Our base is going to be 5. So what do we know? We know for sure it's going to be increasing. It's going to have a vertical asymptote at the y-axis. It's going to go through the point 1, 0, and also 5, 1. So let's put those together. Okay, vertical asymptote here at the y-axis goes to the point 1, 0, and it has the critical point, or the key point, 5, 1. And then we can put those three pieces of information together and kind of connect it to make a curve. All right, let's do some transforming. So the good thing is these are going to be the same transformations we've been talking about for polynomials, for exponentials. Now we're just going to do it for logarithms. We're going to shift it, stretch it. Everything's going to be the same. Let's just think about what it'll look like in these graphs. So here, if we shift it to the left, right, it's going to look like x plus c. Our equation will look like x plus c. So what shifts to the left? Well, the vertical asymptote shifts to the left c units. This critical point, 1, 0, moves to the left c units. This critical point, B1, moves to the left c units. And then we just draw a line connecting them, a smooth curve connecting them. Same thing if we have x minus c, it's going to be a shift to the right by c. So vertical asymptote shifts, the x-intercept shifts, this key point shifts. Okay. All right, so sketch this graph, log base 3 of x minus 2, alongside its parent function, meaning log base 3 of x. Include key points and asymptotes on the graph. Okay, so our parent function, log base 3 of x, is going to look like this blue one, right? Our y-asymptote is, our vertical asymptote is at the y-axis. We have the key point, 1, 0, and the x-intercept 1, 0, and the key point 1, 3. So all of these are going to the shift to the right by 2. So the vertical asymptote becomes x equals 2. The x-intercept becomes 3. This key point becomes 5, 1. So let's see, the domain used to be 0 to infinity. Now the domain is going to be 2 to infinity. The range hasn't changed, and the asymptote moved from x equals 0 to x equals 2. All right, what about shifts up and down, right? Plus or minus d at the end. Again, vertical asymptote is not going to change. This point, 0, 1, or 1, 0, right, is going to shift up. So we have this point B1 on our original graph. It's going to shift up by D. We don't have to worry about those points. We would just shift this 1, 0. This would go up to 1 plus D. Or sorry, it would still be at 1 D. And this would go from B1, it would go to B1 plus D, right? And if we shift down, it's going to be the same. So let's look at an example. All right, log base 3 of x minus 2. So it's going to be log base 3 of x, which we just graphed in the last one, shifted down to. So here's our original function, the blue one. We've got our x-intercept, our y, our key point. It's all just shifted down by 2, right? The vertical asymptote hasn't changed. So the domain is still 0 to infinity, range negative infinity to infinity. The asymptote is the same, the x-axis. Vertical stretch. Okay, so it doesn't change the asymptote, right? So a vertical stretch is going to be where we have a coefficient out here, a, right? So if it's bigger than 1, it's a stretch. If it's between 0 and 1, it's a compression. So the location 1 and b are not going to change of our 2 key points that we care about. Just this one, the y-intercept the x-intercept will stay the same. This 1 is going to become a. So let's look at an example. 2 times log 4 of x. All right, so the blue function is log base 4 of x, vertical asymptote at 0, at y equals 0, x-intercept at 1, key point at 4, 1. Okay, we have a vertical stretch of 2. So this the x-intercept stays the same, vertical asymptote doesn't change. The location of this point doesn't change. We just multiply the output by 2. Okay. All right, let's put them together. So we've got a shift to the left by 2 and a shift to the left by 2 and a vertical stretch by 5. All right, so log base 5x is the red one. Okay, there's our original function. So vertical asymptote at the x-intercept, or the y-axis. Sorry, let me start over. Vertical asymptote at the y-axis, x-intercept at 1, and key point at 5, 1. Okay, so let's shift it to the left by 2. Vertical asymptote is going to shift to the left by 2. The key points, this x-intercept is going to shift to, should be a negative 1. It'll be here at negative 1. And this one shifts over from 5, 1 to 3, 1. And again, that should be at 1. All right, so now we're going to shift to stretch that function by 5. Our x-intercept does not change. Vertical asymptote does not change. This point at 3, 1, we're going to multiply by 5, which this should be at 3, 1, right? Because this 5, 1 shifted over. So I think that these graphs aren't base 5. So sorry about that. Oh, either is this. It's not base 5. Let's start over. This is log base 10. Okay, so x-intercept still the same. Vertical asymptote is still the same of our original function, but it's supposed to be at 10, 1 is going to be our key point. So, all right, shift to the left by 2. Our key point is going to go to 8, 1. Still can't see it. But our shift to the left, the x-intercept still changes. When we stretch it, the x-intercept doesn't change, right? And we could extend our graph to include the key point, or we could just plot a few other points to get an idea of what the graph looks like. All right, how about reflections? Reflection about the x-axis. So here's our base function, log base b of x. Reflection about the x-axis is going to be minus log base b of x. It's going to look like this. It'll be decreasing. About along the y-axis, here's our original function. Here's the reflection if the minus sign is inside the parentheses. So graph this log of minus x, log base 10 of minus x alongside its parent function. All right, here's our original function, x-intercept at 1, a key point 10, 1. That should be a 1, not 0. If we reflect it across the y-axis, everything is just going to reflect. This becomes -1, 0, -10, that should be a 1. And the vertical asymptote has not changed, right? It's still at x equals 0. All right, so let's just think about this without having to graph it. There's a bunch of stuff going on here. What is the vertical asymptote? So let's think. The original function, log base 3 of x, the vertical asymptote's at x equals 0. So let's see, this is a horizontal shift to the left by 4. That will change it. That'll change the vertical asymptote to be x equals -4. This stretch won't change the vertical asymptote. This reflection across the x-axis won't change the vertical asymptote. And this shift up by 5 won't change the vertical asymptote. So this horizontal shift is the only thing that changes the vertical asymptote. So it's going to be at -4. All right, what if we go the other way? We want to find a possible equation for the common logarithm function graphed here. All right. So what are the first things we can observe here? The vertical asymptote is at -2. So the original function had to be shifted to the left by -2, right? We also know there's going to be a reflection. If our original function went like this got reflected about the x-axis. So we could put a negative sign there. So that leaves us, we don't know what A is, our vertical stretch, and we don't know what our vertical shift is. So how can we find those? Let's look at some points that we have. It passes through the points -1, 1, and 2, -1, right? So those are 2 points that we can kind of grab hold of. And so let's substitute the first point in to this equation here. So -a times log -1 plus 2 plus k, that gives us log of 1. -a times log of 1 plus k equals 1. What is this? Log of 1. We're going to talk about properties of logs next time. But 10 to what power equals 1? 0, right? So this term goes away, and we find that k equals 1, right? This is using the fact that log of 1 is 0. All right, so we found k. That's good. So now let's plug in the other point. -1 equals -a log 2 plus 2 plus 1. There's our k value. Okay, well, log of 4, we subtract the 1, we get -2 equals -a log of 4, divide by log of 4, or negative log of 4, and we get that a equals 2 log of 4. We could put that in our calculator. We could leave it in that form. But we plug this back into our equation, -2 over log of 4, log of x plus 2 plus 1. Okay, so some of these things, like the horizontal shift, we could find just by looking at the graph, right? The vertical stretch and the vertical shift, we had to use 2 points on the graph to find. And that's the end of this section. So in your homework, you're going to be doing these things, transforming logarithmic graphs. So the key thing, there's 3 things to remember: the vertical asymptote, the x-intercept, and the key point at B1. Okay, let me know if you have questions.